All right, also on the 5.03 quiz is going to be lesson 5.02, which is about, again, tying into collision theory, but also what sorts of things will make a reaction happen faster. All right, so you'll be able to list these things, and then a key term you're going to want to make sure you're familiar with by the end of this is the word catalyst. All right, so just a quick review so that we know kind of what's going on inside of a reaction here. We talked in the last recording about the fact that in order to cause a reaction, the reactants must, so what do the actual chemicals have to do? They have to collide with a certain amount of hopefully you're thinking the word energy. All right, so that collision has to be strong enough. And what's the technical term for that energy? All right, it at activation or activates the reaction, so activation energy. All right, good little review here. In terms of applying this to a rate of a reaction, as we got to think about how quickly this can happen. All right, so rate of a reaction is going to be the time it takes for the concentration of your reactants to decrease. All right, so do they decrease at 1 mole per minute, 2 moles per minute? Like what? How long does it take for a certain amount of your reactants to disappear? Or how long does it take for a certain amount of your products to appear or increase? All right. Something that you can think about here is what are some things that you think, just go before we even move on to a list, what are some things that you think might have an impact on how fast a reaction takes place? All right. I mean, we know you've got to have the actual reactants there. All right. So probably having more of them might make it go faster. We know that they need to have a certain amount of energy, so if we can provide a way for them to have more energy, that might make it go faster. All right, so there's a whole bunch of different things. You're going to want to get this list down. All right, so these are the 5 things that you need to be aware of as far as how they affect the rate of a reaction. All right, these are things you probably had an intuition on. All right, so if you have more of your reactants available, they're more likely to collide with each other. All right. So having a higher concentration of your reactants will make it go faster. Temperature, we know that as we increase temperature, that increases the energy of our molecules, so we're going to be more likely to hit that activation energy. I will say we're going to talk about temperature in more detail later. All right, there is a balancing act. Too much temperature for some reactions can actually be a bad thing. But in general, all right, compared to running reactions close to absolute zero, all right, so just like normal like room conditions, if you're able to increase the temperature by a few degrees, that should make your reactions go faster. At the extremes, sometimes it's a little funky. Particle size, all right, this is related to the fact that, if you're trying to react sugar, you're going to be better off having sugar in smaller particles, so like powdered sugar versus cubes of sugar, just like with dissolving. All right, so if you can have more surface area, the collisions are going to be more likely to take place. So smaller particles are better because there's more surface area spread out among all the teeny tiny particles instead of just the surface area of the cube. Pressure, right? Higher pressure is going to force molecules into smaller spaces, which is going to make them more likely to collide. All right, this is especially important for gases, just like it was with dissolving. And then the new one, this is the important one to pay attention to, is catalyst. All right, so what a catalyst does is it decreases the activation energy required. So it's a chemical that makes it so that you need less energy to get to that transition state. All right. Now, something to keep in mind, that a catalyst is not one of the reactants of your reaction. All right, it is a chemical, but it doesn't get used up in the reaction. It just kind of like, it's like a wagon that brings the chemicals together, but the wagon itself isn't one of the reactants. All right, so this is not a reactant. It does not actually react at all with the chemicals. It just kind of facilitates the reaction and makes it so that it's easier to get the chemicals into that transition state. All right, and it's really what it does is it just makes it so that you need less energy to get the transition state to take place. So a visual of what it looks like when you have a catalyst going on is your reaction rate diagrams, the hump shrinks a little bit. All right, so let's label this diagram. We know our reactants are going to be at the beginning and our products are going to be at the end. All right, and our transition state is always at the top. Helps if I spell things right. Transition state is always the top of the hump. All right, for the red diagram, let me change. Our activation energy is going to be from here all the way up to the top of this one. This is an uncatalyzed reaction. But you'll notice if we throw a catalyst in there, the blue hump represents the catalyzed reaction, so that transition, that activation energy decreases. All right? And then your enthalpy, you'll notice for either one of these, it's the exact same because your reactants, and I'm sorry, this R looks more like a K right now. Your reactants, which are over here, and your products, for both the red and the blue line, are in the exact same spot. So your enthalpy is going to be the difference between your reactants and your products. All right, so there's your delta H. That's the same for both of them. All right, so the only thing a catalyst does is change the activation energy. It makes it less, which means you'll need less energy to get to that transition state. All right, one last little kind of review thing here. Is this exothermic or endothermic? Hopefully you said exothermic because your products are at lower energy than your reactants, which means some energy was given off. All right, so if you're having a hard time with these reaction rate diagrams, let me know. Stick around. Otherwise, you're good to go. And take that 5.03 quiz.